Let f sub 1, f sub 2, f sub 3, be a sequence of real-valued, Borel measurable functions defined on R. Let f be another real-valued, Borel measurable function defined on R. We say that f sub 1, f sub 2, f sub 3, converges to f almost everywhere and write the limit as n approaches infinity of f sub n equals f almost everywhere. If the set of x in R, for which the sequence of numbers f sub 1 of x, f sub 2 of x, f sub 3 of x, does not have limit f of x, is a set with Lebesgue measure 0. (1) Mathematical deconstruction. The definition operates on three critical components. The sequence Fn, a series of functions f1, f2, f3, that evolve or refine over the index n. The target f, the limiting function that the sequence is attempting to reach. The domain X in R, the input space, real numbers, over which these functions are evaluated. The logic. Standard pointwise convergence requires that for every single x, the sequence Fn of x must eventually equal f of x. Convergence almost everywhere relaxes this strict constraint. It states that Fn of x must approach f of x for all x, except for a specific set of bad points. The condition. The convergence is valid if and only if the set of bad points, where the limit fails, has Lebesgue measure 0. The measure of the set where the limit does not equal f of x is 0. What is measure 0? In the context of the real line, measure is intuitive to length. An interval 0 to 1 has measure 1. A single point has measure 0. A countable collection of points, even an infinite list like integers or rational numbers, has measure 0. Implication. A function can fail to converge at an infinite number of specific points, yet still converge almost everywhere, provided those points do not aggregate to form any continuous length or volume. 2. Financial intelligence analogy, the high-frequency pricing model. To intuit almost everywhere versus everywhere, consider the performance of a high-frequency trading algorithm relative to the continuous flow of market time. The domain X, a continuous trading session, from 9:30 to 1600. Time is treated as a continuum, not discrete ticks. The sequence Fn, a derivative pricing engine that is being updated to perfectly track the theoretical fair value of an option. The target f, the true, arbitrage-free fair value of that option. Scenario, the glitch. As the algorithm upgrades to n infinity, it tracks the fair value with absolute precision for the entire day. However, due to a hardware quirk, the algorithm outputs a price of $0 at exactly two distinct timestamps. 10 o'clock precisely, 14:30 and 5 milliseconds precisely. The assessment. Pointwise convergence fails. If you look strictly at the timestamp 10 o'clock, the model is dead wrong. It does not converge to the fair value at that specific point. Convergence almost everywhere holds. The duration of a single instant is 0. Even if there are multiple discrete error points, they possess no width in time. The probability of randomly sampling a moment in the day and landing exactly on the error is 0. Strategic insight. In financial modeling, convergence almost everywhere is the standard for viability. We accept that models may break at singularities. Measure zero events, provided they hold true for the measurable continuum of the market. The bad set exists, but it carries no weight in the integral of returns.